Hello and welcome to the first video on Java Puzzler series. So in this series, I'm going to add multiple videos where there will be some Java puzzlers, and then we'll see the what's, the whys, the hows behind it, and try to understand the internals of Java through these puzzlers. Okay, this is the first puzzler, and it's pretty simple one. So what you see here is some calculation that is happening, and we are printing the result of that calculation. If you want to answer the question about what the output will be, you can pause the video here. And then, well, let's try to guess what the output will be of this program. So what you see is a simple calculation, 2.8 minus 2 into 10. 2.8 is a double, 2 and 10 are ints, and the output will be double, but then that's casted to int, and then we print the int output. 2.8 minus 2 is going to be 0.8 into 10 will be 8. So what you see is I should be 8, and then that's what you would expect in the output. So we expect that the output will be 8. So now run the program and then see what happens. If I run it, I get the output 7, and that's really surprising. Now let's try to understand why the output is 7. Okay, so to understand why the output is 7, we need to understand how doubles are represented in memory in Java. Any fraction or any double can be represented as this: significand into base to the power exponent. For example, this number 1234.625 can be represented as 1.234625 into 10 to the power 3. The idea here is to move this decimal point to the left so much that we have only one digit to the left of the decimal point, which is a non-zero digit. So in this case, it is 1. And for that, we had to move the decimal point 3 places, and therefore the exponent is 3. This is in decimal system. Now let's convert this to binary system. There should be another video about how to convert fractions from decimal to binary. It should be somewhere on the screen, or you can find the link in the description. So this in binary becomes 100,100,100.101, right? And we can also represent this in the significant base exponent form, and therefore this becomes 1.00100100101 into 2 to the power 10, because we had to move the decimal point 10 digits to the left. Now let's convert this part into binary. 2 in binary becomes 10, and 10 in binary becomes 1010. Now let's convert 2.8 from decimal to binary. In binary, this becomes 10.110011001100, and this goes on. And in our format, we can represent this as 1.011001100 dot 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 into 10 to the power 1, because we only moved the decimal point one place to the left. And this is how 2.8 can be represented in binary. Now what we notice is that in order to represent 2.8 in binary precisely, we need infinite number of digits, because the 1100 part goes on repeating, and we need infinite digits to represent it precisely in binary. This is actually the problem, and we'll see later on why this gives our calculation a wrong result. Now let's see how a double is represented in memory in Java. Java reserves 8 bytes or 64 bits to represent a double. Those 64 bits are divided into 3 parts. So the first part is a single bit, which is used to store the sign of the number, because the number can be positive or negative. Then the next 11 bits are used to store the exponent, and then the remaining 52 bits are used to store the significant. So in total, these digits are 64. These bits are 64. And also, if you look at this representation, you only need to store significant and exponent because we know what the base is going to be. And that's why in the memory representation, we only have significant and exponent being represented. Now let's see how 2.8 would look like in memory. It is a positive number, therefore the sign bit is going to be 0. 0 is used to denote positives and 1 is used to denote negatives. Significant part. So the significant part is going to be this part where the first digit is always going to be 1 and therefore that doesn't need to be stored in memory because we know it's always going to be 1. The remaining bits are stored here, char 0, 1, 1, 0, 0, 1, 1, 0, 0, and this goes on until 52 bits. The exponent, which is this part, can also be positive or negative, but we don't store the sign in a different bit. But what we do is we add the exponent to 1023 in decimal, and the result is stored in the exponent bits. So in this case, this is going to be 1 plus, well, 10 times 1, and the result is 1 followed by 10 zeros. And therefore, this number is stored in the exponent part. So this is how 2.8 looks like in memory. Similarly, let's see how the number 2 is stored in memory. It is positive, so sign is 0. Significant is going to be all zeros, and exponent is going to be same as 2.8. Now let's see how 10 is stored in binary. 10 in decimal is nothing but 1010 in binary, and therefore this becomes 1.010 to 10 to the power 3, which is this. So this is how it will be in binary. And now let's see how this will look like in memory. Positive, therefore 0. When we add this to 1023, then we get this. Significant is 010 followed by lots of zeros. If you look at this 2.8, we are not able to represent it precisely in binary. This number is almost equal to 2.8, but it is actually something like 2.79999. Yeah, but this is not exactly 2.8. The number 2 we are able to represent precisely. Similarly, the number 10 we are able to represent precisely. When you do the calculation, uh, the double calculation of all these three numbers, so 2.8 minus 2, and then the result multiplied by 10, what you get is a number very close to 8, but not exactly 8. So we get 7.9999999999, and that is because the number 2.8 we are not able to represent precisely. This result, when it is casted to int, what we get is 7, and therefore the outcome of the program is 7. Okay, now that we have understood why the calculation shows a wrong result, let's see how we can correct this. Now that we have seen why the output is 7, let's try to see how we can get the correct output. Now there are two ways to achieve that. One is by knowing the limitations of this calculation, use a workaround or use a system to work around that problem or those limitations. So in this case, what we can do is use math dot round, which takes a double and gives a long, which is the nearest integer to the double that is given as input. We can cast it to int and then we can print the int. So this would then change the output to what we want. Right. Now there are also limitations to this because there are many ways to round numbers and we may not want the nearest integer, but maybe something else. So we need to see if this is really what we want. The second way to solve this is to use a more precise type to store these numbers, which becomes extremely important when we want to have very precise calculations, let's say involving money. So that data type is big decimal. What we can do is we can use big decimal to represent all our let's say values here. So 2.8, let's say we call this PD1, and that is a big decimal corresponding to 2.8. Similarly, we can create another big decimal corresponding to the value 2, and we can create one more corresponding to value 10, and then we can use these variables in this calculation. So what we will do here is bd1 dot subtract bd2 and then multiply by bd3. Now this gives us a big decimal, so we can actually use the big decimal to also store the result and then print the result, in which case we will also get our desired outcome. But then we note that this is also a fraction. If we really want an integer value, we can get that by calling int value on the big decimal, which gives us an int the way we expected. And then if you run this, we will get also the outcome that we desired and in int form. So basically the summary of this video is that floating point calculations or double calculations may not always give us the exact result that we want, and therefore know those limitations and use other ways to achieve the calculation that we want, or to use big decimal if that is a possibility, because big decimal is more precise and then we can use them to make the desired calculations. Hit like if you liked this video. Also, if you have questions, put them in the comments. I will try to answer them there or create new videos. And if you like this content, consider subscribing. And thanks for watching, and I'll see you in the next video.